Okay, so this chapter is going to be concentrating on formula masses, empirical molecular formulas, and molarities. So here are our objectives. What are we doing? Okay. So the first thing that we're going to look at is our formula masses in the mole. So the formula mass, remember when we figured out the average, excuse me, the average atomic mass? When we figured out, we looked at the isotopes and we had to figure out the weighted average. So that's also going to be what we call our formula mass. It's just how much an atom weighs. And so we're going to look at these, and if it's an atom, we call it a formula mass, and if it's a molecule, we call it a molecular mass. It's totally okay if you exchange those two words. So molecular mass, atomic mass, they're all just looking at the periodic table. So they're referring to the decimal number on the periodic table that we've been using. We're just going to be using it a ton now. So if you look at the periodic table, so on the periodic table, if we look at carbon, right, it says like 12.01, hydrogen says 1.008, chlorine says 35.45. So to get the molecular mass, also called the formula mass, all we do is add those three things up. So if we have CCH3, this one weighs, hold on. This one weighs 12.01, this one weighs 1.008, and this one would be 35.45 times 3. So all we did was add those three things up. And move that out of the way. Okay, and so we look at this. So if someone asks like, what is the molar mass or the formula mass or the molecular mass? All we do is look at the periodic table, add up the decimal numbers. So we're going to be doing this a bunch. So here's another one. Here's an ionic compound. So if we have NaCl, so if we're looking at the periodic table, so Na says 22.99. And again, Cl is 35.45. All we need to do is add these two numbers up, and that is our formula mass. So the word formula mass, just so you know, it's specifically referring to ionic compounds, where molecular mass is referring to molecular compounds, but they are the exact same thing for our purposes. All we're looking at, the decimal numbers on the periodic table, adding them up. That's all we're doing for these. Okay, so our next concept we're going to learn is what's called a mole. And I have a fun shirt. I'll wear it next time for us. So if I said, how many shoes are in a dozen? Say 12. If I said, how many donuts are in a dozen? 12, right? How many chairs are in a dozen? 12. So the word dozen to us means 12 things. It doesn't matter what those 12 things are. A dozen always means 12. So if you get a dozen eggs, how many eggs are in there? 12, right? That never changes. Same thing with the word pair. No matter what I say, if I say a pair of shoes, you're like, oh, that's two shoes. If I said a pair of pencils, you'd be like, oh, that's two pencils. Well, in chemistry, we have a new word that we're going to learn, and that word is a mole. And a mole means that there are 6.0221367 times 10 to the 23 things. Yeah, we're going to simplify that number a little bit. So if I said, we're going to simplify it, by the way, in just a second, to 6.022 times 10 to the 23. So if I said, how many shoes are in one mole? Well, there's 6.022 times 10 to the 23 shoes in a mole. If I said, how many donuts are in a mole? 6.022 times 10 to the 23 donuts in a mole. That's a lot of donuts. If I said, how many chairs are in a mole? 6.022 times 10 to the 23 chairs in a mole. So when I say a dozen, what number do you think of? 12. If I say a pair, what number do you think of? 2. If I say a mole, what number do you think of? 6.022 times 10 to the 23rd. So this is going to be a chemistry thing that we're going to use all the times. And by the way, you do not need to memorize that number. It will always be given to you. So you'll always see this conversion here that I have in red. It'll always be written out for you. Okay, so what a mole? Well, a mole is just a unit that we're going to use, similar to a pair, a dozen. By the way, does anybody know what a gross is? It's actually 144. Well, you do not need to know that. It's just like fun little fact that nobody knows. So where did we get this number 6.022 times 10 to the 23? So a mole is the amount of substance containing the same number of discrete entities as the same number of atoms in a sample of pure carbon-12 weighing exactly 12 grams. Like that's just a lot, okay? So what is a mole? A mole is the amount of anything that has as many things as there are atoms in 12 grams of carbon-12. So if I asked you to go and get 1 atom of carbon for lab, you'd be like, no, because that's impossible. But if I asked you to get 12 grams of carbon in lab, could you do that? You could. You could get 12 grams, right? We've used the balances. We can weigh out 12 grams of carbon. Absolutely. Now, in that 12 grams of carbon, there is 1 mole of carbon. And again, how many things are in 1 mole? In 1 mole, there are 6.022 times 10 to the 23 things. So if we have 1 mole of carbon, how many atoms of carbon are in there? 6.022 times 10 to the 23 atoms of carbon. Sorry about the handwriting. So the reason we use a mole in chemistry is because we can't do anything with an atom. We can't react 1 atom with another atom. They're just too small. We can't do it. But we can react a mole of something with a mole of something else. So 1 mole of carbon weighs 12 grams. All right, so we're going to work on this one as soon as I can get my PowerPoint to start behaving. Okay, so this brings us again to Avogadro's number. Now, Avogadro's number again is like, it's a big number. But we call this Avogadro's number because the person who figured it was Amadeo Avogadro, which we'll talk about him more. But we kind of abbreviate it to this. So this number is the number we're going to be using a bunch. And so how this works is 1 mole of anything has 6.022 times 10 to the 23 atoms in it. So a mole of anything has that number of atoms in it, no matter what. And so every element has different masses, so they're going to weigh differently. So let's look at kind of how this works. Okay, so each of these samples, so we've got zinc, you can't see this, we've got carbon, zinc, magnesium, copper, sulfur, silicon, lead, and tin. Now, you're going to notice these numbers here are the same numbers from the periodic table. So if we looked at zinc right here, if you look at zinc, it's like 65.4 something-ish. We have them rounded. So that's what we have here. These are the numbers from the periodic table. But each of these are 1 mole. So again, how many things are in a mole? 6.02 times 10 to the 23rd. So each of these represent 6.022 times 10 to the 23rd. But if you look at them, they don't weigh the same, right? Look how much less carbon weighs than zinc. Well, if we look at the periodic table, let me get the actual numbers here. So if we look at carbon, carbon is 12.01 And if we look at zinc, zinc is 65.38. Okay, why does carbon, so in each of these, this is 6.02 times 10 to the 23rd atoms of carbon. This is 6.02 times 10 to the 23rd atoms of zinc. Why is carbon weigh less? What's the difference between zinc and carbon? So we know from our first exam, all atoms have protons, neutrons, and electrons, right? So what's the difference between the protons, neutrons, and electrons of carbon and the protons and the neutrons and electrons of zinc? Does carbon and zinc have the same number of protons, neutrons, and electrons? They do not. Which one has more protons, neutrons, and electrons? Zinc. Zinc has more protons, neutrons, and electrons. So therefore, zinc is heavier. So when we have 6.02 times 10 to the 23 atoms of zinc, it weighs more than the same number of atoms of carbon. So think of it like this. If we had ping pong balls and bowling balls, we agree, different masses, right? Now let's say you have a dozen ping pong balls. How many do you have? 12. And you have a dozen bowling balls. How many do you have? 12. Which one weighs less? Ping pong balls, right? A dozen ping pong balls weighs less because ping pong balls are lighter. Same thing here with carbon. The carbon atoms weigh less. And so therefore, if we have 6.022 times 10 to the 23 of them, they're going to weigh less than the same thing of zinc. So if we look here, if we go to like, for example, like look at how much lead weighs. So 6.02 times 10 to the 23rd atoms of lead weighs a ton. It weighs, we're just going to write 207 here. Because if we look at the protons, neutrons, and electrons for lead, it's got 82 protons. So lead is like our bowling ball, really heavy. So why do we use this thing called a mole? It allows us to be able to react these atoms in lab because we can't do anything with atoms. Like if I say, go get an atom of lead, you'd be like, how? But if I said, go get me a mole of lead, how much lead would you bring? 207 grams of lead, right? That we can work with. So the mole just allows us to go from the micro world of we can't experiment with this to the macro world that we live in. And it's always that many atoms. So it's like a giant dozen. So now when we look at the molar mass, that's this number that I've been writing on the periodic table, our imaginary periodic table here. So the molar mass is the definition of it is I can't read this over here. So it's the mass in grams of 1 mole of the substance. And it's always going to be in grams per mole. So for example, if we look at carbon, I can't remember where I think it's on the other side on your periodic table. It's right here. So 6.01. Remember this number right here, that 12.01, that was the weighted average. Remember how we took the weighted average of the different isotopes? And so this is the number we're going to use. It's got all of our isotopes in it. So if I asked you, how much does 1 mole of carbon weigh? 1 mole of carbon is 12.01 grams of carbon, right? Now, if I asked you, how much does 1 atom of carbon weigh? 1 atom of carbon is 12.01 AMUs. So this symbol of AMU, that just means atomic mass unit. So this means atomic mass unit. That's if we talk about a single atom. But again, are atoms useful for us? No, not really. So we're really never using AMUs. we're just really never going to use it. We're going to use moles. We're always going to use moles. Okay, so we're going to practice with these. So again, what we have here, here's an AMU, atomic mass unit. This is 1 atom. This is 1 mole, right? So when we look at the molar mass, we're always looking at 1 mole, and we look at AMU, atomic mass unit, that's 1 atom. But do you see these numbers are exactly the same? But this is always going to be 1 single atom. How many atoms are in here if it's 1 mole? Anybody remember the number yet? 6.022 times 10 to the 23 atoms. So that's how many atoms are in this number, which we call, again, we call this the molar mass. Now, this means whenever we look at the periodic table, so I'm just going to keep using carbon here, this decimal number on the periodic table, the units are always grams per mole. So the units of 12.01, that's 12.01 grams per mole. That's what that number on the periodic table is. So whenever you see the periodic table and you see the decimal number, there is a unit attached to that number, and that unit is going to be something we're using from now until the end of the semester. And that unit is grams per mole. Now you can see this. So it's grams per mole. So we're going to practice with this. Okay, so if I said, how much does a mole of oxygen weigh? What would you say? 16 grams. But if I said, how many atoms are in 1 mole of oxygen? 6.02 times 10 to the 23rd atoms. So how much does a mole of sodium weigh? 22.99 grams. But how many atoms are in a mole of sodium? 6.02 times 10 to the 23rd. So that number, 6.022 times 10 to the 23rd, it goes for all of them. So remember, the reason these numbers are different is because they have different numbers of protons, neutrons, and electrons, so they weigh different. They have different masses. Okay, so now what we're going to do is we're going to calculate the difference. We're going to go from one thing to another. So we're going to be doing conversions. So do you remember when we did like centimeters to meters and grams to milligrams and how we're always doing conversions? We're going to use that same process, but now we're just going to do it using the periodic table itself. And we're going to be using our number from our periodic table. So in this case, this one's specifically asking about potassium. So if we have 4.7 grams of potassium, they want to know what that is in moles. So if we look at potassium, because we don't have a periodic table, potassium is 19 and it has 39.10. Okay, so it says 39.10 on the periodic table. So again, what are the units of this 39.10? It's 39.10 what? Grams per mole, right? That's what that 39.10 means. It means grams per mole. So remember, this line right here is the same thing as this. 39.10 grams per 1 mole. That's how we're going to use it. But remember, we could also use it another way, because we can flip this. We can say in 1 mole, there's 39.10 grams. And I should probably be more specific and put a K here for potassium. Both of these unit conversions are exactly the same. We just need to decide which one we're going to use. So just like you did when we learned how to do our unit conversions before, we always start with the number they gave us. What was the number they gave us? 4.7 grams. And 4.7 grams of what? Grams of potassium, right? 4.7 7 grams of potassium. Okay, now, what do we want here? They asked for the potassium in moles. Okay, so do we want the unit grams? Nope, we want to get rid of it, right? So when we want to get rid of a unit, what do we do with this unit? Where do we put it? On the bottom to get rid of it. Because remember, we want to cross this unit off. Okay, so now, knowing that, are we going to use the one on the left or the one on the right to get rid of that unit? The one on the right, because grams are on the bottom. So we're going to use this one on the right. So we'll put 39.10 grams of potassium, and on top will be 1 mole of potassium. Because again, what we want to do is cross off our units, right? So that's why we put it on the bottom. And then we get our answer, and our units will be moles of potassium. So we're going to use this conversion just like you used every other conversion, but now we're getting the number from the periodic table. That's the only difference here. Otherwise, same thing you did before. Now you just get the number from the periodic table. So if we do this, here's our answer. It's the same thing. It's just prettier and nicer and neater. We end up with 0.12 moles of potassium. So now here's our sig figs. They're back. How many sig figs are in 4.7? 2 sig figs. So how many sig figs do we have in our answer? 2 sig figs. That's supposed to be SF for sig figs. So now our calculators are going to give us bazillion numbers, and we need to pick out how many. So remember, we're never going to use our molar mass. We're always going to have less sig figs than our molar mass, so you can just ignore these when you're looking at sig figs. So just look at the number you started with for significant figures. Okay, so now we're going to try another one. Okay, so when we're looking at this one, again, we always have to start with the number they gave us. What number did they give us? No, go back. They gave us 9.2 times 10 to the 4th moles of argon. Okay, so that must mean we're dealing with argon. So we look at our periodic table. We look for argon. Argon is number 18. And it has 39.95 at the bottom of it. Okay, so we always have to start with the number they give us. Okay, so we have 9.2 times 10 to the negative 4 moles of argon. Okay, what unit do we want in the end here? It says, what is the mass of argon? What unit is mass? Mass means grams. Grams. Mass means grams. Okay. Yes. We'll very, very rarely use AMU, especially with the word mole. We'll never use it. So AMU always means specifically one single atom of it. And so since this says moles here, that's a hint that we're not going to be using AMU. You'll rarely ever see AMUs. Very rarely. Okay. So what unit has to go on the bottom? Here. What unit are we trying to get rid of? Moles. So that means moles of argon has to go on the bottom. So now we have to look, and what unit do we want? Grams. So grams, the question is, can we go from moles to grams? We can, because remember, this 39.95 from the periodic table, what are the units of this 39.95? Grams per mole. That is the units. Those are the units. That number means grams over moles. Every time we look at the periodic table, that's the units of the periodic table. Sorry, that keeps happening. So remember, this 39.95, we can write it in two different ways. We can say 39.95 grams of argon in 1 mole of argon, or we can say 1 mole of argon over 39.95 grams of argon. Okay, so which one are we going to use, the left or the right? Does everyone agree that we're going to use the left? The reason we're using the left is because moles is on the bottom, and we want moles on the bottom. So that means we put in 1 mole of argon, and on the top, 39.95 grams of argon. And again, our units will cross off and wind up with grams. Now, when we put this in our calculator, how many sig figs will we have in our answer? How many sig figs is this? 2. So how many can we have? 2. But your calculator is going to give you a whole different answer. So make sure put that in your calculator, because it's a good test of how good you are with your calculator. Because now you're going to see we're always going to have exponents everywhere. So when we put this in our calculator before we round, what do we get? 0.0, give me a bunch of numbers. 3, 6, 7, 5, 4, okay, and a bunch of other numbers, right? But we can only keep 2. So which 2 shall we keep? The 3 and the 6. But what's the 7 going to tell us to do? Round up. So we're going to round this to 0.037 grams of argon. And that is our answer. So do you see how we're using our sig figs and our rounding with the calculator now? So we're kind of doing everything. We're doing the same thing we did before. The only difference is we're getting the numbers from the periodic table now. It's the same thing as we're doing from centimeters to meters and such forth. Okay, any questions on this? How are we feeling on these? Because we're going to do some. Okay, so here's the same thing, just prettier. There it is, much prettier than I had. Remember now, whenever you have a number, you have to have a unit. So 0.037 without this would be incorrect. 0.037 grams without this, without argon, would also be incorrect. You need to have the entire thing to be correct. So the units and what we're talking about. So grams and argon each time now. Okay, here's one for you to try. So this time, I give you a little extra little thing. You got to add these up to get our molar mass. So try this one and we'll go over it in just a minute. Okay, so first thing we have to do is add our molar masses. So when we look, right, carbon is 12.01. Oh, let me make that neater for you. Hydrogen is 1.01. Oxygen is 16. And nitrogen is 14.01. Now, depending on what periodic table you use, some of them have more than 2 decimal places after the number. That's fine. You can use more than 2 decimal places. You just can't use less than 2 decimal places. So you couldn't just say carbon is 12 and nitrogen is 14. You have to use at least 2 places past the decimal. The reason is because when you have really big numbers, if you round them all, your molar masses will be really far off. Okay. Now, if you want to use more than 2 past the decimal, like if you look online, you'll see some of them have like 3 and 4. You're welcome to, but just make sure you use at least 2 places past the decimal. Okay, so when we do this, we have 2 carbons, so we're going to have to multiply that one by 2. 5 hydrogens, so we're going to have to multiply that one times 5. 2 oxygens, multiply this one by 2, and then just 1 nitrogen. So when we do that, our molar mass ends up being 75.07. Now, if you did use a number that had more than 2 places past the decimal, like you're going to see here, oh no, yeah, I used these ones that had more than. Do you see how this one I used 1.008? And this one I used 14.007. It's okay. Your number's just going to be a little bit far off. So for those of you that used our periodic table, did you get 75.07 or what did you get? 7.08. It is totally acceptable to have a molar mass that's a little bit different because, as you can see here, this one I used 3 places past the decimal, and this one I used 3 places past the decimal, which made my number 75.07. But if you only used 2 places past the decimal, then your number was 75.08. That happens all the time. So if you use a little bit different numbers on the periodic table, that means your answers are also going to be a little bit off. That is super common and absolutely okay. You're not going to get the exact same answer every time, but your answer will be very close. And when you're doing your active chem and your quizzes and things like that, it's okay. That difference is figured into your answers. So it's okay if you use more than 2 places, but you can't use less than 2 places past your decimal. Okay, so when we do this here, again, this number, now if you use 75.07 or 75.08, remember this number means grams over 1 mole. And it's grams of C2H5O2N over 1 mole of C2H5O2N. And yes, you do need that part, right? So you do need the label to go with the number, right? Or again, we could have written it like this. 1 mole of C2H5O2N over 75.07 grams of C2H5O2N. Both of those are correct, but which one are we going to use? Are we going to use the one on the left or the one on the right? So what number are we starting with here? Grams of glycine. So when we write this, we have 28.35 grams of C2H5O2N. So therefore, what unit has to go on the bottom here? Grams has to go on the bottom. Does everyone see how that works? This is why we were so crazy. I was like, you have to write your units. You have to write your units because now you have to write your units. So that means, are we going to use the one on the left or the one on the right? Which one has grams? We have grams on the top, so we want the one that has grams on the bottom. So which one has grams on the bottom? The one on the left or the one on the right? The one on the left. I know, with my horrible handwriting, sorry. This one has grams on the bottom. So that's the one we're going to use. This one has moles on the bottom, so we're not going to use moles. We want grams on the bottom. So when we do this, oh, by the way, before I put the answer up, how many sig figs can we have in our answer? 4, because this 28.35 has 4 sig figs. So because it has 4 sig figs, our answer has to have 4 sig figs. So let me just erase all this. I'm trying to figure out how to make this faster. And look at my sig figs aren't correct. I have 3. So this should be 0.37 what? 76 moles of glycine, which is C2H5O2N. And it's totally okay, by the way, if you write the word glycine or the symbols, it's whichever one whichever one you want. If you just want to write glycine, that's okay. Okay, how are we feeling on these? Okay, this is kind of the basis, by the way, of all chemistry math. Like, this is what we do all the time. In Chem 219, this is what you do the whole time. You just use different things and you add up different numbers from the periodic table and you just combine them. This is kind of the basis of the whole thing. So that's why we're kind of making sure we understand it. Okay, so here's one more for you to try. So I want you to try this one. This time, I gave you the molar mass. So you'll notice that after a while, we'll just start giving you the molar mass because once you get good at adding it, it just takes a lot of time. So I want you to try this one, and then we'll go over it in just a minute. So if we start with the number that they gave us, right? So they gave us 1.42 times 10 to the negative fourth moles. That's the number they gave us. So that's the number we're going to start with. So if we write that, we have 1.42 times 10 to the negative fourth moles of vitamin C. So you can either write C6H8O6, or you can just say vitamin C. This is your choice. I think in the key I did vitamin C, so I'm going to do it this way. C6H8O6. It's really annoying. Okay. What unit has to go on the bottom? Moles. Moles has to go on the bottom. And what do we want to get to? It says, what is the mass? What unit is mass? Grams. So we have moles and they want grams. Whenever we have moles and they want grams, the unit of the periodic table is always grams per mole. So if you have moles and you want grams, or if we have grams and we want moles, we're always going to look at the periodic table because that's the units of the periodic table. So those two always go together. It's going to be really important because pretty soon we're going to switch it up and add a new one. Grams and moles, periodic table every single time. So when we do this, we're going to put moles on the bottom. It's always 1 mole and then 176.124 grams on the top. And I have it much nicer here. And this time I just wrote vitamin C because it made it easier. And again, we have 3 sig figs. So we have 3 sig figs. We do need that 0. Right? Because if we just did 0.025, that's only 2 sig figs. We need all 3. So our answer is 0.0250 grams of vitamin C. So the next 2 exams and your final, you're going to be doing this all the time. So it's kind of like your new standard thing we do in chemistry. So we're going to work on these a bunch to make sure that we understand them. Okay, any questions on any parts of this? So if you see grams and moles, where are we always going to look? Periodic table. Grams and moles, always look at the periodic table every single time. Okay, so the next thing we're going to do is we're going to add something to it, but we're going to take a break there.